All right. I will begin with a word of prayer. So, we can get up here. Heavenly Father, we thank you for this day. Again, I thank you for this class. I just ask you to help us to glorify what we do, and that we all understand a little bit more about differentiation today, Lord. In your name I pray, Lord Jesus. Amen. So, I'm going to circle back to, how to do more calculations and interpreting things and so forth. But just to get this out of the way, this is sort of more theoretical bit. And so I think it serves us better for me just to kind of walk through the notes with you guys and try to explain the proof to you. Thanks, sir. And so I'm trying to find my other laser. I may have to use this one. Oh, there it is. All right, so what is meant by continuous differentiability? So first of all, we need to unravel something that may be bouncing around in your head, which is this seems like a redundant phrase, because we learn in Calculus 1 that if a function is differentiable, then it's continuous, right? One of your homework problems asks you to show that if a mapping, if you will, is Frechet differentiable, then it's continuous. That's true. So what do we mean by continuous differentiability? We're not speaking of the differentiability, we're not speaking of the continuity of the function, we're speaking of the continuity of the derivative. And that's up for grabs. You can have a function which is differentiable, and yet the derivative itself is not continuous. That's a separate question than continuity. So continuity of the function. Is that a boba? All right. So continuity of the function and continuity of the derivative are different. Okay, I mean, I prefer boba to well, I don't know, what does a boba look like? A liver? I was thinking more like a rabbit turd, but let's see here. Enjoy your boba. So, so here's a function from the reals to the reals that I found from this is an advanced calculus book by Hubbard and Hubbard. I believe it's a husband-wife team. And Hubbard and Hubbard, this advanced calculus book, it has the weirdest examples of anything. It's great. It's a great book. But one of the examples I found in this book was this function right here. F of x equals to x over 2 plus x squared sine of 1 over x. That's what it's defined for x not equal to 0. For x equal to 0, it's just 0. All right? Now, you can prove, and I'm not going to, that the derivatives of this function exist at 0. And in fact, this function is differentiable everywhere. And it's even differentiable at 0. And the derivative of 0, it happens to be 1/2. All right? But that has to be proved with some somewhat delicate arguments because, well, anyway, I'll shut up. So you can prove the derivative is a half. All right. But on the other hand, if you calculate the formula for the derivative anywhere but 0, just differentiate, right? 1/2, product rule, 2x times sine of 1 over x minus, hey, where'd my x squared? Oh, duh. Times the derivative of sine of 1 over x, which gives me a cosine of 1 over x squared, times the derivative of 1 over x, which is minus 1 over x squared, and the x squareds, they be canceling. So that's why there's no x squared over here, which is very much a problem at 0, because as you approach 0, this does not go to 0. This goes to plus or minus 1, viciously so. Right? So this derivative is not continuous at 0, even though it exists at 0 and is equal to a half. So this is one of the quintessential examples of a function which is differentiable at 0, but not continuously differentiable at 0. Here's a graph of what's going on. The function f is this red curve, and the derivative, you can't see it very well in the projector, because the projector always kind of doesn't do well in green. I like green, though, so I'm not giving up on it. I don't care about the projectors. So eventually projector technology will catch up with decent color schemes. But anyway, so the point is that's the graph of the derivative, and as you can see, it's very, very far from continuous at 0. It's oscillating at 0, right? What this means is that the tangent line at 0 is not really a very accurate approximation for the function at 0, right? Because you'd like here's something that you'd like. if the function's increasing, the tangent line should be increasing, right? Because the tangent's supposed to be a local approximation to the function, isn't it? Not for this thing. On any neighborhood of 0, you can find, it to be increasing. You can find neighborhoods where it's increasing and decreasing as many times as you like. If I like little subintervals, it's always increasing, decreasing, increasing, decreasing. It's just very, 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 very wiggly at the origin. So the tangent line doesn't really do it. So this is a function which is, again, not continuously differentiable. Now, that phenomena continues to happen for functions of more variables. You could have it happen for functions of more variables, all right? And so, obviously, you can see how that could get you into some trouble. Let me go on here. This is an example of this function. Oh, goodness gracious. This is Maple, but as you can see, it's a superior image to Mathematica. Sorry, I created this a long time ago, but I think this function has partial derivatives, partial f, partial x, and partial f, partial y, which both exist, right? And you can, so this function's continuous at the origin, and both the x and y derivatives, the function's identically 0 along the coordinate axes, and which means that if you calculate partial f, partial x along the coordinate axes, they're both 0 because the function's constant on the coordinate axis. So if you calculate the partial derivatives on the x direction or the y direction, they're both identically 0. But this is the partial derivative everywhere else, all right? And these, so these functions. So what I'm trying to say is, the partial derivatives exist at the origin, but there really isn't a well-defined tangent plane. And the reason for that, in part, is because these functions are not continuous. These functions actually are not continuous at the origin. And you can kind of begin to appreciate what's going on here. So you've got like the functions level here and here, but there's not really a tangent plane at the origin because it's ripping. The tangent plane kind of rips up and down, and it's just, there's not a tangent plane, honestly. Although I guess I shouldn't say that. I mean, it kind of depends on how we define things. Maybe you could say the tangent plane exists, but it's not a good approximation to the function at the point. That's probably more honest. Anyway, so here's another sort of nefarious example. This one here has all directional derivatives exist at 0, and yet the tangent plane at 0 doesn't exist because it can't exist because of this blue hair that kind of sticks out. It ruins their being a tangent plane. Anyway, so let me go on here. Let me get to the point. These are just some counterexamples, some troublesome counterexamples. So all of these have to do with discontinuity in the derivative. So what do we mean by continuity of the derivative? Well, technically speaking, we should be talking about A maps to dfa as continuous. In other words, saying limit as x goes to a of dfx equals to fa. But this is exactly the part of the course which I won't test on because this is the infinite dimensional linear algebra part. All right, so in order to define the norm of an operator, we have to use the operator norm. The operator norm is judged by the supremum of the norms of the operator taking in unit vectors. And as such, you get this, but then if we have differentiability, we can trade that for partial derivatives, and we get this. So what this all means is if we do know that the limit as x goes to a of partial f partial xi at x is equal to partial f partial xi at a, then that allows us to prove that the limit as x goes to a of the differential of x is equal to dfa. What I'm trying to say, let me put it into words more precisely. This is what we'd like to mean by continuous differentiability in the Frechet context. This little calculation right here shows you that it suffices to know that all the partial derivatives are if all the partial derivatives are continuous at the point, it follows that we have this sort of continuity. All right? And so for that reason, we make the following definition. A mapping from Rm to Rn, from Rn to Rm, is continuously differentiable at A and U if and only if the partial derivative mappings d sub j of f, which of course you could also denote like partial f, partial x sub j, right? So the partial derivative mappings exist on an open set containing A and are continuous at A. So continuous differentiability of a map is judged by continuity of the partial derivatives of the map. All right. From a pure math perspective, this is a little bit awkward because directly speaking, we ought to judge continuity of the map in terms of continuity of the differential, but this is not a big deal because of this calculation. It says that in fact they're the same idea. So what does continuous differentiability do for you? Well, it gives us this theorem. This theorem is a big one. It says that if f is, so first of all, I proved the theorem in the case that the mapping is real valued. If you can prove it for that, then you can easily extend the proof to vector valued. So it's easier just to prove it for a real valued map and then from that extrapolate up to like a vector valued map. But anyway, so if we have continuous differentiability of this mapping, then that implies differentiability. So so here's the difference. Continuous differentiability is a statement about partial derivatives. Partial derivatives are easy to calculate, as we will soon see. All right, the rest of class is going to be that mostly. But differentiability is that Frechet quotient, which is a multi-dimension. It's like a multivariate limit, right? That's a little bit tough. And so the way this works is as follows. We consider a plus h sufficiently close to a, such that all the partial derivatives of f exist. All right. So what we're going to do is we're going to start at a, and we're going to go to a plus h by following let me draw the picture for this in like 3 dimensions maybe. So I'll put a here just for the sake of making my picture easy. So I start at a, I go to a over here, a plus h1e1, right? That's p1. So it's just moving in the x. And then I go over to here. Let me try that again. I go over to, whatever. I go over to here, which is, this is p1. This is p1 plus, h2e2, which of course would be a plus h1e1 plus h2e2. Right, that's the step. So I go from here to there, then to there, and then up I go, up and away to here, like so. And that brings me to, what did I call it? Well, I guess in my current nomenclature, it would be P3, which is P2 plus, H3E3, also known as, in particular, A plus H. So this is what the picture of this construction looks like when we just have 3 coordinate directions. But the argument which I'm giving, this is an n-dimensional argument, all right? So, so if we can see that there. I'm going to scooch back up here. Well. So, should have worn my glasses. I got new glasses, but they're in my office, so. All right. Okay, so we go P0, P1, P2, all the way out to Pn, which is A plus H. So the thing to notice here is if we look at the difference of any two successive steps, right? That difference in these pair of steps, right? They only involve one coordinate changing, right? So like Pj minus 1 ends up being A plus this minus A minus that, which the A's, they be canceling, and you just have, well, Hj, Ej, all right? And so we can, take the difference of f of a plus h and f of a, and we can write it as a sum of the differences between each of these successive steps. So like n to n minus 1, n minus 1 to n minus 2, p1 to p naught, right? So I just added 0 a bunch of times. That's all that is, right? Because notice that f of p naught is f of a. All right, that is f of a. So each one of these differences we can encapsulate with the mean value theorem. Because the mean value theorem relates the change in the function and the average, the change in a function to the value of the derivative of that function at some point along which you're changing. But a partial derivative is just a derivative. So the mean value theorem applies to these partial derivatives. And so like mean value theorem gives me that hj partial j of f of this is equal to the change of f between pj and pj minus 1. Now, I'm not sure exactly, but there's got to be some point along that little segment at which the average rate of change is matched by the instantaneous rate of change. That's the mean value theorem. So this mean value theorem produces this c sub j, right? Which puts this point where this equation is attained somewhere on that line segment between those two successive points. So therefore, using the mean value theorem, for each interval we can select c1 through cn such that this is true. F of a plus h minus f of a is equal to the sum j equals 1 to n of h sub j partial j of f at those points which are supplied to us by the mean value theorem. So our goal at the moment is to use the continuous differentiability to prove that the function's differentiable, right? So to do that, I have to do what? I have to propose a differential, which is a function which is linear and satisfies the Frechet quotient. My proposal is we just reverse engineer what we derived last class in the easier direction. The easier direction last class was suppose it's differentiable, calculate the directional derivatives. And we saw that in that case that there's a relation. And basically the relation was just to build the differential from a sum of the partial derivatives like this. So I just try to, do the weave the partial derivatives together. And, but not anybody can do this. You got to be intelligent to do the weave, right? Well, that's not really true. You just need to know the mean value theorem on each step. So I didn't prove the mean value theorem. Somebody else proved it first. Do you guys know about the weave? Don't know about the weave?
I know about some weaves.
You got to watch the interview with Trump and Rogan from a little bit before the election. That's where he talks about the weave. You got to be smart to do the weave. Awesome. It's the absurdity that he's president. I mean, I voted for him, don't get me wrong, but he is nevertheless, not long ago, the guy who did cameos in Home Alone 2 and, The Apprentice, anything. And isn't he better than all of the career politicians, though? Look what he actually does. I don't know, but anyway. Well, we'll see what he does. Yeah.
Anyway,
Thank you. This is math. We're going to go back to math. Very good.
Wait, so how did you get from the mean value theorem to doing the weave again?
So the mean. So this is the difference. So we have f of a plus h minus f of a. It was equal to that sum of things up here. This right here is the mean value theorem. So we have partial f partial x sub j is equal to, of that point, is equal to f sub pj minus f sub pj minus 1 divided by hj. H sub j is the change along that particular segment. So, where was I? So we have this. I propose that this is the differential. So we take the difference of f of a plus h and f of a, and when we plug that in, we have this. All right. But remember, we have up here f of a plus h is that, right? Minus that is this. So I'm taking that and putting it here for this. but L sub h is that. Then I combine the sums, which leaves me h sub j times the partial derivative of f in the jth direction at this point, minus the jth derivative of f at a. But in the limit h goes to 0, all of these different segments squish down to a, which means all of these c sub j's basically have to go to 0. And by continuity of the partial derivative, this has to match that, which shows that this has to go to 0, which is to say that we have the Fauché quotient satisfied. So so I mean, here's the formal argument, limits this is that, but that gives us this, and then we can argue that this has to limit to 0, and this right here is actually bounded. So you have something bounded times something that's limiting to 0, which gives us a 0 limit. I probably have more jibber jabber past before I can scroll down to. Yeah, here's the rest of the jibber jabber. So if I take the norm of that, it's less than or equal to that, but that goes to 0, therefore the differential exists, and it's given by the sum of the partial derivatives in this way. So yeah, that's the theorem, and we can extend it, and here's the argument for the extension. I won't bore you with that, but if we have a function that goes from Rn to Rm, if continuously differentiable, then f is differentiable at a. Notice the difference between this theorem and the last. It's just that I've got a vector rather than just r. And the proof basically, I think it's just the vector limit, because I know if I have continuous differentiability of each component, if I have differentiability of this mapping altogether, that means I had continuous differentiability of each component function, which means I can then use the previous theorem and build the derivative for each component, and then I just put those together, and that gives me the derivative for the whole thing. That's all this is saying. So. I got superscripts in here? Oh, son of a gun. Yeah, sorry about that. In manifold theory, we tend to start putting indices up. These are not powers. This is just like another notation. You'll see this sometimes in like physics books too. If it's a contravariant index, they'll write it upstairs, whereas a covariant index you write downstairs. But it doesn't mean anything in particular here. It's just another notation for the jth component. So, sorry, sorry.
Well, they probably did it because of the BFA.
Because of the what? Is this a joke?
There was another subscript.
There's a subscript.
Oh. So it was, yeah, all right.
So it would have been weird to do
All right.
DJ or DFJ.
Let me find my notes. All right. So listen, what this theorem I just proved is super nice, because what it means is that if we have partial derivatives which are continuous, we can just put them together and form a differentiable function. So we don't actually have to go through the annoying, rigmarole of checking that Fauché quotient actually limits to 0. We can just kind of like look at the functions, component functions, and go, oh, okay, well, these are continuously differentiable. Yay, we've got a differentiable map. And so that's like very labor saving in practice. But there's a formula I need to share with you guys before I forget. I've talked about it, but I need to write it down, which is specifically what is the differential in terms of the partial derivatives. All right, so here it is. So, and this is a little bit more general, so you'll forgive me. I will write a few things in terms of norm linear spaces, but we're almost, I said we're done, but sorry. The real norm linear spaces where beta equals to v1, v2, vn is basis for v with coordinates x1, x2, xn if f mapping from domain of F, which is a subset of the vector space V to W, is differentiable at A, and H is equal to a sum, I equals 1 to n, of H sub I, V sub I. So H sub I are like the coordinates of H with respect to the beta basis. Then dFA of H, the differential of F at A of H, is equal to the sum I equals 1 to n of H sub I partial F partial X sub I of A. We actually use this to calculate the derivative of the square map last time. We calculated it two ways, right? I calculated it by looking at like A plus H and squaring it, and then subtracting F of A and isolating the linear part, and then arguing it directly satisfied the Fauché quotient. That was like one of the examples we did last time. And then I calculated partial derivatives of that same map with respect to the Aij coordinates, right? And we put those together, and we found the same differential. The way I did that was to use this formula. But when I did that, in that example last time, you got to understand what's going on. So like last time, the Aij, played role of X sub I here. So there are examples where the index that describes the vector isn't just a single index, right? If you're going to describe a matrix, the natural coordinate system to use is just like the component of the matrix, which you don't want to just list out. If you have an m by n matrix, there's mn coordinates, right? And I guess you could list those as like x1, x2, x3, all the way out to xmn, but that would be horrible. It's much better to say xij or aij is the coordinate of a matrix. That gives us a more natural coordinate system in that context. That was the example we did last time. But if you look at what I did, and of course let me just write it down. So last time we had like df, whatever it was. I guess, I can't remember what point I did it at, but I guess I could do it at A I used big H for the matrix, and it looked like this, right? Sum I and j of Hij partial F partial Aij at A, So this is the same theorem, but in the notation where we're putting a double index on the basis, because the basis is matrices. So like labeling matrices is just more natural to use that kind of label. Right. So sometimes I do that kind of thing without thinking. And if I do that kind of thing, you're confused, ask me. There's a follow-up to this theorem though, see, because we can say more. Remark, if partial f partial, x sub I is continuous near A, then df A exists and is given by star. Here, we'll make this famous. There you go. Yep.
What is H in that?
H is, well, the differential acts on a vector, but here the vector is a matrix.
It's acting at A.
We calculate the change in the function at a point, but then with respect to an increment. So h is playing the role of the increment. Like differential always involves a point at which you're calculating the derivative, but also an input to measure a corresponding output. There's always two things.
So that would go to 0.
It's like the directional derivative in Calc 3. We calculate the directional derivative at a point in a direction. So h is like the direction, a is like the point.
Okay.
That better? Don't ask me to draw the picture for the matrix one, but you know. All right, so anyway, I just wanted to point out that the theorem we just proved, I proved it for Rn, but that theorem can easily be proved in the context of a norm linear vector space by almost the same argument. All right. So I'm not going to do that, don't worry. I'm just going to claim it works. So getting back to a function, which is, say, a mapping from Rn to Rm, right? We have the differential of f at a of h is equal to the Jacobian of f at the point A times h, where the standard matrix, if you will, the standard matrix of the differential is equal to the Jacobian. All right. The standard matrix of the differential is the matrix of the Jacobian. Now, the standard matrix of a linear transformation is obtained how? So like here's side comment from linear. So here's some linear algebra for you. If we have T as a mapping from like Rn to Rm, then the standard matrix of T is, we obtain it from like TE1, TE2, TEn. Where here E1 through En is the so-called standard basis. It's the basis we talked about on day one. It's got 1 in the, you know, E sub I has a 1 in the ith spot and zeros elsewhere. So like, for instance, if we calculate the, you know, column J, let's say, of the standard matrix of the differential, what that would be is we take dfa and act on ej. We take the differential acting on the j standard basis. We talked about last time that that is equal to the partial derivative of f in the xj direction of a, right? So let me put this together for us. So the Jacobian matrix of f is actually going to be like partial f, partial x1, partial f, partial x2, partial f, partial xn. So this is a, you know, if this is an m by n matrix, if f is a mapping again from Rn to Rm. So let me do one with an actual formula in it. Let me find one that's reasonably interesting. I have too many examples in the notes to write on the board, right? There's lots in the notes for you guys to read in terms of like, you know, additional examples. I think technically example 2.3.16 is the solution to one of the problems in your notes. Just saying, 2.3.16 on page 44. Oh, so for mission 2, now you got options, right? Well, I guess it depends on my wording. I do want you to do the Fauché quotient if I say to do it, but if I don't say to do it, what's the way to do it? That way, right? So let's do it that way for an example. All right, so suppose I have f of x1, x2 equal to, oh, I don't know, cosine of x1, x2, comma, x1 divided by x2. So there's a mapping from R2 to R2. Tell you what, let me make it more exciting. We'll make it go all the way over here to R3. Ooh, yes, x1 plus 2x2. There we go. I'm done. I'll stop. So this is a column. This is a column. So it probably would be helpful for the calculation to rewrite it as a column. You'll see why in just a second. So we've got cosine of x1, x2, x1 divided by x2, and x1 plus 2x2. That's my function. So this is what I would call f1. This is f2. This is f3. These are the component functions of f. So here's the Jacobian matrix of f. We got ourselves partial f, partial x1, partial f, partial x2, and that's it, because we've only got two variables. And how do you calculate those? Well, there's no secret like new-fangled, oh, this is advanced calculus, so you take partial differentiate different here. No, it's the same partial differentiation you already know from calculus 3, and or have forgotten from calculus 3 because you took it a while ago. But let's assume that you are going to remember it. Let us shake the rust off our brain, and we would get x1 differentiates. I get a minus sine of x1, x2, and I'll write a step out here. Partial x1 of the inside function. And then this one gives me 1 over x2. I'm changing my x2 to an x squared. That's not a good sign. And then this one just gives me 1. Next column, I get minus sine of x1, x2 times the partial derivative with respect to x2 of x1, x2. Then I get minus x1 over x2 quantity squared, and I get 2. All right, I'll clean it up. So what is the answer? What is the answer here? The answer is minus the sine. Oh, my bad. I like to write the, when we take the partial, I'm going to do the wrong one. Over here. What's the partial derivative of x1 with respect to x1 of x1, x2? It's just what? Just x2. So I do minus x2. I'll write that first because that's just better, you know? So minus x2 times sine x1, x2. And then this one gives me minus x1 sine of x1, x2. And I've got a 1 over x2 here. And I've got a minus x1 divided by x2 squared there. And then finally 1 and 2. And this is the Jacobian of f at the point x1, x2. All right? So where is this function differentiable? Let's analyze it together. Where is this function differentiable? So you say not on the axes. Well, I don't have any trouble with x. I mean, x1 equal to 0 is fine. I don't mind that. But your heart's in the right place. x2 equal to 0 is trouble. x2 equals to 0 must be avoided, right? Because we have division by 0 there, right? And as such, the partial derivatives are not continuous along such points. But everywhere else, you see, if we look at u is equal to, let's say, x1, x2, such that x2 is not equal to 0, then f is continuously differentiable on u. How do I know that? because the Jacobian has all of the partial derivatives. They're all there. Look at them. Behold them. They're beautiful. As long as x2 is not 0. In which case we're in trouble. Trouble, trouble, trouble. Otherwise, differentiable. And we can write down the differential if we wanted to, right? What is it? So the differential of f at the point, let's call it at the point a comma b, if we put in h comma k, it's the Jacobian of f at the point a comma b times the vector hk, which is, oh, I regret this example, minus b sine of ab 1 over b 1 minus a sine ab. I'm not going to multiply this out, so you can deal 2. But this is the formula for the differential of f at ab acting on increment h comma k. If I wanted to linearize this function, I could use this to form the linearization according to the formula we talked about last class. I will not do that because we have other fish to fry today. So let us do another example. How about let's see here. What if we have R is a mapping from, say, R to Rn? Then the Jacobian of R is equal to what? So, by the way, I like to, usually we, well, let me write out what R is. So we usually use this notation. R is equal to, like, x, y, z. Oh, I'm sorry, we did n, didn't we? My bad. x1, x2, xn, right? So as a column vector, we've got these component functions for my vector valued map. This is what we call a path or a space curve in Calculus 3 sometimes. What's the Jacobian matrix of this? So the Jacobian matrix, so in this kind of context, I like to say at time t, let's say. And it's kind of silly. It's, well, I guess we could say partial r, partial t, but this is where the notation kind of like breaks down a little bit. Because we wouldn't usually use a partial notation here, right? Because there's only one independent variable, we would typically just write dr dt. And yeah, that is, of course, the you should recognize this. This is the velocity vector of the path. And the differential of r at time t, if I feed it h, then it is simply h times r prime of t. Because this is r prime of t, right, in our usual notation. Differential. Now, let's see here. On the other hand, oh, wait a minute. Haha. The other interesting kind of function to look at involving Rn, how about what if we have like f, big F, which goes from Rn to R, right? So what I just wrote down might be a parameterization of a path in Rn, right? It might be a parameterization of a path. But we might also have like a level surface kind of thing in Rn. Well, I guess this would be a hypersurface technically, but if I had x1, x2, dot, 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 xn equals to, say, 0, I could look at that kind of thing, right? That would describe a hypersurface. So, I mean, up here, I didn't really talk about this, but up here, so here's x1, here's x2, here's x3, x4, all the way out to xn, right? There's my, who says you can't graph n dimensions? I just did it, it's right there, right? And so this right here, going on and on, is R of R. It's the image of it takes the real line and it pastes it up there into some sort of curve in Rn. That's what a parameterization does. It pastes the real line onto this curved line. In contrast, this thing, if I was to foolishly try to draw it, I'll do a different picture. Here, this is my picture of Rn. x1, x2, x3, xn. Here's another picture of Rn. And the level surface might look like, I don't know, this. So there's f of x equal to 0. If you'll let me use x as a vector. I'm briefly breaking from the calculus to talk about what these things could be understood to be, all right? If we take 3 dimensions, if we're talking about f of x, y, z equal to 0, well, that's a level surface, right? We looked at that in calculus 3, I think. So what's the Jacobian of such a map, right? So let me dial it back a second here. So we're looking at f going from Rn to R. So the Jacobian of f is what? What size is it? This is, by the way, R1, right? So we're looking for a 1 by n, a 1 by n matrix. This one went from R1 to n. This is a n by 1 matrix. That one was a column. This one will be a row. And so in this context, we just have like partial f, partial x1, partial f, partial x2, partial f, partial xn. You might recognize this. Now, technically speaking, I might call this the gradient of f. However, my gradient is a column vector. Since my gradient's a column vector, I'm obliged to put a transpose on here to make it into a row vector, all right? Because the Jacobian matrix is definitely a row vector here. So how does the differential work in this context? Well, if I take the differential of f at a point, let's say P, and I feed it a vector h, I'll call it h vector just to emphasize it's a vector, then this is going to be, the Jacobian of f at the point P times h, which, by the way, would be the gradient of f at the point P, transpose times h. But by the way, a column vector transpose times another column vector, I keep losing my vectors. They are decoration after all, but this is the formula you know and love from calculus 3, the dot product of the gradient of the level function with the vector. So the directional derivative is calculating the change in the function at P in the h direction. So this Jacobian does what? Which derivatives does it cover? The answer is yes. All right, like it's everything. Where was I? Let me go on here. Let me do another one here. So, how about this? If R parameterizes f of x equals to 0, right? What I'm trying to say is that T maps to R of T is path on solution set f of x1, x2, xn equals to 0. Like, what does that mean to say it's a path on the solution set? What that means, guys, is that when we plug in the parameterization into the defining condition for the surface, or this generalized volume, it's a hypersurface technically, it works, right? So like, it should be the case that f of r of t is equal to 0, right? You did this in Calculus 3. You had like a parameterization of a curve. You plugged the parameterization into the formula, checked that it worked, right? I'm just saying that in general, that idea. So, all right, great. How do you take the derivative of something like this? Well, here's how we would do it in view of the chain rule we talked about last time. Let's just forget about the equal to 0 for a second here. Let's talk about how to take the differential of a composite. So we take the differential of f composed with r. The theorem that we had last time said this. It's df. I guess I have to say at which point. Say at time t. So it would be df at r of t composed with dr at time t. That's the chain rule. Now, let's see here. You guys tell me, what's the deal here? If f is composed with r, what are we doing? We're going from r to rn back to r again, right? So this is really a mapping from r to r. So if I look at this as a matrix equation, I should have the Jacobian of f composed with r is equal to the Jacobian of f at r of t times the Jacobian of t for r. This, we have to understand, is nothing more than d dt of f of r of t. Now I'm going to use the last two examples. The last two examples. We just learned that the Jacobian of f for f is the gradient of f, and we have to evaluate at r of t. That's the inside function. We take that, we transpose it, right? And then this was dr dt. Of course, maybe you recognize this formula, maybe you don't, but this is the gradient of f at r of t dotted with dr dt. This is the chain rule for multivariate functions that we learn in Calculus 3. It might be more familiar if I wrote it out in components. In 2 dimensions, it looks like this. Partial f, partial x, dx dt, plus partial f, partial y, dy dt is equal to d dt of f of x of t, y of t. That is the chain rule, the multivariate chain rule. If you re-express that as a dot product and look at it what it is in terms of being a dot product between the gradient of the level function and the derivative of the parameterization, it's exactly the dot product of the gradient and the derivative, just like that. But this is the n-dimensional chain rule. That's the 2-dimensional version. What else did we do in Calculus 3 that we might review? Maybe help us understand this stuff better. What other thing did we parameterize? Oh no, what have I done? Is f a vector? Oh no. Goodness gracious. That's offensive. This is why I should just, I mean, I knew enough not to put it over here, but goodness gracious. All right. See if I have. All right, so I have like a kabillion examples of Jacobians. Please just like read page 44 and 45, and you should be able to, I think we'll all understand. There's not, I can ask you to calculate Jacobians all day long, and I'm just giving you points, right, for the most part. Yeah. Now, oh yeah. So I don't want to. I want to project this one because it's a lot for me to write out. I have some better chain rule examples. So, I was very happy to find this when I first taught advanced calculus. It all of a sudden started just coming to life to me that all of the different chain rules I teach in Calculus 3, they're all this same chain rule that we proved last time, just in different contexts. It's always just really the chain rule. And so like the heart of what's going on here, guys, is that this is the composite of two linear transformations, right? And so when you calculate like two linear transformations, T1 composed with T2, and you calculate the standard matrix of those, well, what happens is you get the standard matrix of T1 times the standard matrix of T2. So the fact that the chain rule says that the differential of a composite of two functions is the composite of the differentials, what that means then is that the same is true for Jacobian matrices. Like the Jacobian matrix of the composite is the product of the Jacobian matrices, because this is how linear algebra plays with composition. But what that means, more to the point, is that I can derive all of the chain rules that I know and love from, oh man, oh, okay, back. So I got to go back. The continuous differentiability stuff is actually after the calculations. I was just encouraging you to read. But, so like all of the wonderful multivariate chain rules that I learned in Calculus 3, they're all really just matrix multiplication of Jacobian matrices. That's all they are. Like here, I think we may have already done this one. I don't know. Let's find out here. So here I'm looking at a function from R2 to R, and then here I've got a function from R3 to R2. We haven't done this one yet. So a function from R3 to R2, this is something you would never have looked at in Calc 3, except perhaps some like weird chain rule end of chapter problem or something, you know. But what that means is you've got x and y, both functions of u, v, w. If that's the situation, then your mapping is going from R3 to R2. So the Jacobian matrix, by the way, so this notation is yet another notation for the Jacobian matrix. Like we can also write, so forgive me, I've written that. So the Jacobian of f, we could also write as f prime. That's the notation which is used in Edwards' Advanced Calculus book, which is the first book I used to teach advanced calculus. So you still see some of that notation residually in things I've written. All right. But anyway, so that's just the Jacobian. But look at that's the Jacobian matrix, right? Well, I say it's the Jacobian down here, so that's a hint. But so partial x partial the u derivative, the v derivative, the w derivative, right? So, by the way, notation. Didn't do the notation here, but I would encourage you guys to think about this notation. If we're going to map like this, we're going from R3 to R2. Something we can do to help ourselves keep track of what we're doing is to go u, v, w, x, y. And that helps me think, oh, okay, so my R3 has u, v, w coordinates, and my R2 has x, y coordinates. You know, that's just a nice notation to organize things. And that maybe helps you understand what's going on here. So like the u derivative, the v derivative, the w derivative, that's the first, the second, and the third coordinates. And so there's the Jacobian matrix for R. Now f is just from R2 to R, so that's kind of like what we just talked about a minute ago. That's just got a 1/2 Jacobian, partial f, partial x, partial f, partial y. Now if I take the composite of f and R, which I can do because they're composable, right? Then I would find the Jacobian matrix of the composite by simply multiplying the Jacobian matrices of the functions composed. And so that